before for sure it would have been detected. And again, it sounds like an obvious thing to ask, but here's a problem. You're asking, you're trying to make probabilistic measurements for data that have not been observed. And statisticians do not like this. There is a, if you don't have data, I mean, frequentists like it because, the data that you get is just one realization of infinity of realizations. But Bayesians tend to just use the data as measured. But even in the frequentist case, you still have to, ask the question, how bright. The confidence intervals in a frequentist case is much more complicated. We don't want to go into that. So, but however you manage to find this, however you manage to figure out what how bright it should have been, then it has to be fainter than that. That seems obvious, right? So far, so good. How do you do that, though? So typically, what do you do for detection? I mean, you usually find, you look at some background that you measured from different ways, you estimate it somehow. And you ask what is the probability that any signal that you get could not simply be a fluctuation from this background. So you set a threshold on the data at some specified significance. Usually this is the 3 sigma significance, right? I mean, this is what we're all used to. It doesn't have to be 3 sigma, it could be anything that you feel comfortable with. And then given this threshold, what you can do is compute the probability for, you assume, for a given brightness, okay? For a given true brightness, you calculate the probability that your probability distribution has how much mass does it have above or below either of this threshold. So this is just basically reiterating that. So this, if you all use, I'm sure you use wave detect. In that case, the threshold is set by limiting the probability of false sources that you expect to see. But in any case, there's a standard threshold that you can always use. And for this, there is this concept of false negatives, also known as type 2 errors, in contrast to false positives, which are type 1 errors. What this is simply the probability that for a given detection threshold, if you do have a true source, what are the chances that you won't see it? Okay. So I will not go through the math for this one again, but let me just point you to that paper and to this figure from that paper, actually. So this is like the probability distribution that you're using to set this threshold from the background. Okay, so this is basically the S in this case is any sort of function of the data that you're calculating. It could be just as simple as counts. Okay, so this could just be counts, and you have given a certain background value, then you have a certain distribution, and you set your threshold such that in this case, such that you are expecting a 10% false positive rate. And then for the, similarly for the true source, you calculate the same probability distribution, and then you ask how much of it falls to the left and to the right. And the important thing here is this value of beta, which is the integral to the right of the threshold. So keep an eye on this. So it's the same figure as before, but it's going to sort of give you some sort of a notion of how things might change. So again, this is at 68%, 95%, and 99.7%. And again, these are just counts. And remember, and notice that I've put in M sub s instead of N sub s just to remind myself that these are not real counts. These are fake counts. But the probability distributions are still calculable simply because this is the likelihood that you get M counts given the different values of lambda b and lambda s. Lambda b you get from the observation as before, and lambda s is you vary the lambda s according to this value, and these so you can see that as this beta is telling you how much of the power is above the threshold, and these values are where it actually hits the threshold. So what does this mean? So let's look at this red curve. So this is the 95% interval. This is for Antares again. Antares, you saw how little we saw. So I'm quite happy with saying I would accept a 2 sigma detection at this stage. So that is what this level is. And at 2 sigma, the power goes above 50%. That is, you got a chance of detecting it half the time at 2 sigma, when the true intensity is 6.3. So let's so that's basically so 6.3 counts in 24 kiloseconds. So let's see what that means. So for a 2 sigma detection with 50% probability. So this is actually the main thing that I want you to take away from this talk. It is that there are 2 numbers you got to quote when you're quoting an upper limit. One is the significance of detection, and the other is the probability that by how much you'll miss it. So you got to quote both the type 1 and the type 2 errors. So I crunched through some of the numbers to see what that meant. If you had a temperature plasma with temperature 10 to the 6.5 or 10 million degrees, we expect to see that the luminosity should be below that number or below this number. Almost done. So I'll leave you with these the science conclusions that we can draw from the fact that we see nothing. The most important of these is that the LX variable is very small for the B star, which means it's probably not a 2.5. It is probably B5 or later. So with that, I'm done. Thank you.
Thank you, Vinay, for the great talk.
About the 50% probability, isn't that just for the 6.3 count, not for less than 8%?
Yeah. So if you remember Doug's talk from last week, he talked about the units along the axis, right? So the 6.3 here is actually in the units of intensity, the true intensity, not the counts, not the measured counts. So it's 6.3 counts true. I mean, if the source intensity were 6.3 or higher, then we would then 50% of the time we would get more counts than the threshold.
So the problem I have with upper limits, I don't like upper limits just in the general sense, because they assume that you have some a priori statement as to what's a reasonable level of probability. You have to assign that. You have to make a choice, and that makes it objective. Okay, so I'm not crazy about publishing data that or publishing a result and then injecting an objective statement into the publication. So I kind of wondered why people don't publish the actual distributions, so that any person that reads the paper can say, well, I kind of like 95% confidence,
I agree.
or I like 9% confidence. If someone makes another observation later and they say, well, I've got this number, and how likely would it have been consistent with your number, that you got at some time, you would be able to read off the table, or whatever, or a figure or something like that.
Yeah, my feeling is just that, at least the reason that I don't do that generally is simply that there is not enough space or there's not a good enough format to publish them. There's only a limited amount of things you can put in a table, and have, especially if you're doing a survey of some sort. Like think of the Chandra Science catalog, the source catalog, right? You got 10,000 sources, and for each of them you try to make a full distribution, posterior density distribution. Well, you need both the likelihood and the prior. Then it can get very...
Well, if you put in the counts in the background and the counts in the source, then you have the information that you need to
Sure.
derive the posterior probability that you just
Oh,
calculated.
sure. You can. Yeah. Then you're saying you can calculate from first principles using any model that you want. If you have the counts in the source region, counts in the background region, and I agree. That is a very good thing.
I've gone through a lot of papers in the literature where they just publish a limit saying, oh, it's less than this amount, and then tell you the background information that goes into how that limit was calculated, and you cannot recompute it.
Yeah. No, I endorse that view completely.
Sorry to cut it short. It was 10 minutes. Let's thank Vinay again for the great talk.
Thank you. I've reached a limit to the talk.
Welcome Aneta to tell us about narrow features in noisy data.
Hello everybody outside. People are listening to us. So let me see. This is attached. Okay. I don't know which way. All right. And the sticker. Okay, thank you. Actually, I'd like to thank you, the organizers, for doing this seminar this semester. When we started with Task almost 20 years ago, and we did astrostatistics talks, we have ourselves. So 5 people came, and then you had a discussion. So, 17, 18 years later, we have room of good number of people, which is very good. And I think, looking at publications, people are aware more about statistical issues than they were some time ago. So thank you. Also, today, this morning, Astro Age has been launched. And, this is the continuum versus lines. We probably will see many of those data in X-rays. And the questions would be, is there a line or is this just a noise? This is an example of Chandra high-resolution spectrum. And I think Mike Novak is still working on figuring out what is the number of lines he sees here. So I will actually address few statistical issues today. So I will talk about statistical model, because that's something which we have to think about when we do astrostatistics. I point issues in fitting of narrow features and describe tests for presence of the emission lines. Everything which I said is described in 3 papers in very great details, together with the description of the algorithms. So if people are interested, go back and read, because there is a lot of math which goes into the calculations. So statistical model. I will focus on the X-rays data. So this is the physical source of our models, typically. So we have a source here. That's J means in some energy bin of the width delta J. And this is the continuum part, which has some parameters and is distributed in energies in J. Again, and these are the lines. So this is a sum of Gaussian lines, Lorentzian lines, and depending on the distribution, we actually have the proportions of the lines, of the photons which goes into these lines. So that's our sort of physical model. So if you look at the spectrum which I showed before, you can imagine there is a continuum and there is some fraction of the observed photons which went into the lines. In X-rays, we also have to include the calibration files. So we observed counts. Which actually come from the source. So it's the same here. And then we have 2 calibration products, effective era and the response file, which tells you how photon energy 5 kiloelectronvolt was detected by the telescope of the detector. And then there is the background component, which could be just the particle background. So there is some background component to our model. So this is the full expression, model expression, and then we have to define the likelihood and look at the posterior distribution. So in our case, the likelihood is defined here. Again, this is the same counts as in the previous observation. This is the Poisson equation with our data, which is the observed number of counts, and then the model given the thetas, so the parameters of our physical model. So theta could be the slope of a power law, could be temperature of the black body, or plasma temperature, could be anything which describes your source. And in case of corona, it could be non-thermal emission, anything. And then we have the base equation again, and what we have here is the posterior distribution, and we use the likelihood and the priors. In this case, what's interesting is that there is a concept of posterior predictive distribution. This is the probability that we will observe number of counts in the future given our observation. And this is basically the integration over the parameter space of our likelihood and the posterior. And that's a very nice quantity to know when we work with our data and we try to say something about the models. So we have these equations, and what we did in 2001, we basically built this big structured model where we start with the emitted spectrum by a source, and these photons which were emitted are going to be lost during our observation. So you have loss by absorption, you lose some of the photons because of the instrument response or pile-up, and then you also have background. So we have this loss of the data, and the path which the photons take, our algorithms should also take. So we have the source, physical source, and then the procedure which will calculate the sort of the loop like this, because this is our observations, and we will at the end learn something about the physical source later. But that's sort of the structure which one think about when one builds a model of your source. So this is a full structure of the statistical approach to your analysis. It's not only my physical model and the result, it's everything. So the algorithm which goes towards the solution, this has to be thought through as well. So we solved this by doing the MCMC simulations from the posterior, and that's the schematics of what happens. So this is our physical source and the priors. We draw parameters, we compute the likelihood, and we also, looking at the data and calibration, compute the likelihood, and then we accept or reject the parameters and go and update the parameters. This block is actually important because, there are different MCMC algorithms, and I'm not going to talk about all the algorithms out there, but depending on the criteria, you have the definition of Metropolis-Hastings criteria, which basically look at your probability or likelihoods and does the acceptance or reject of the current parameter based on the likelihoods of this tool. So depending on this, you can have different types of algorithms. Also, the way you select the next parameter is important in that algorithm because, you can imagine you do the just simple Monte Carlo and don't have any knowledge of acceptance. You just select these parameters from whatever you think the parameters are out there, and you can draw them, but at the end you would not have a nice solution, because maybe it takes a long time to do that. So you have this criteria which tells you how to move through that parameter space. And they are usually based on the previous solution. So you have previous parameters and the current parameters. You have the comparison, which tells you whether or not to accept, and you move forward. So the draws are not independent draws. There is always connections between those draws. So it's sort of like random walk moving through the parameter space. So you're probably doing this now because the computers are great. So you look at the results and you see this. So usually after you run the MCMC, you have to look at your traces of the parameters, and that's sort of okay. Trace, there are criteria for looking at the convergence, whether or not your chains actually converged. You look at the distribution on the scatter plots of the parameters. So in this case, you see the correlations. You can calculate standard confidence range on it, or distribution on so it's probability density function for one parameter, and you can look at the widths. I'll do this. So this was sort of an introduction, because I don't think Doug was talking in details about it, and we were thinking about having somebody talk about samplers. But I wanted to give this introduction before we get into the lines, because there are some difficulties in using just straight MCMC or straight fitting to do this identification of narrow lines. So this, the standard MCMC can be very slow. And when you say line is very narrow, so the width of the line is really the width of your bin, so it's unresolved. You cannot really fit that line, because when you say, okay, line is there, and I do my algorithm, the line will stay there. It will not move. So it will stay at the initial value. So there was the computational issue right away when we looked at this, and David Van Dyke and Taeyong Park developed some algorithms which were able to deal with that. This is Gibbs samplers and partially collapsed Gibbs. So in that paper, they describe those. The next big issue when you're looking for narrow lines is that you have this multimodal likelihood. So you have a lot of peaks in your parameter space. So you can have lines, scattered across your spectrum. So standard statistics, such as mean, mode, and variance, are not reliable. When I look at my posterior distribution and I see these bumps and I say mean value, you don't know what it means. Or mode, you don't know what it means. So in this case, you usually look at the profile posterior distribution for exploratory analysis, which means you look at the way the parameters behave on one axis, let's say, and look at whether you're really dealing with this multimodal problems. Then in testing for presence of narrow lines, usually there are problems related to the standard test where models are not nested. So you have a line and you have a continuum, and the line intensity is always positive, even if you say it can be positive or negative. If there is no line, there is no location of the line or width of the line. So in the case of the continuum and line model, the line is really at the edge, or it's sort of separated from your model. So the location and the width does not exist in a simple model. They are not nested. More importantly, the sampling distribution of this likelihood ratio test, which we usually apply to the line, under the simpler model is not well understood. The main assumption for the likelihood ratio test is that it will follow the chi-square distribution. But this is not true in the case of the narrow lines in the spectrum. So the solution which Protassov came up with was posterior predictive p-values. So this is the illustration of this more important problem that your chi-square distribution, let's focus on this one. So we have likelihood ratio statistics, which takes the model without the line and model with the line and compare the two. So this is the chi-square distribution which you would normally use for that. And this is the simulated data, which I tell you how you do it in next step. So as you can see, the simulated data which should be coming from the true distribution are very differently distributed than your chi-square. They really don't follow this. We'll come back to this. So the simulations which you do is that in order to see whether the line is detected or not in my continuum, in my spectrum, I have two models. One is without the line, so I have continuum, and one model is with continuum and line, and they are not nested, right? We define the test statistics, so likelihood ratio tests, where we have the likelihood of one model and likelihood of the other model, and we calculate that ratio based on the data. And then I simulate the data, assuming that I only have the continuum there. So using the simpler model, and I fit the simulated data with these two models, one with continuum, one with continuum and line, and then I calculate test statistics on this simulated data. I repeat the steps, 3 to 5, to get a large number of these iterations and large number of test statistics. This has to be very large if your significance is very good, right? So you need to have 10 to 10 iteration to see 10 to minus 9, let's say, in your simulations. Anyway, you can plot this distribution and then compare the observed and simulated test statistics as it's in this graph. So these are the simulations, right? This line comes from the observation of the data, and this number tells me how many, what's the percentage of the data, so what is in the tail, what's the percentage of the whole distribution which goes out, beyond that line. And, this is 2.6%, this is 1.5%, so this is actual value. Oh, and this line shows the 5% in this case, and that's the actual value for false positive. And then this is again the line, and the simulated value is 31.5%. So in these three cases, there are three different models assumed here. So in these three cases, in this case, you wouldn't say that the evidence for the line is very strong, while in this case, you might think about the line being there. And so the summary statistics for the posteriors are here. Vinay actually said about equal tails. So I plot here probability density function for some model parameter, let's say normalization. And you can look at equal tail. So this is 68th percentile. The highest posterior density, if you have a mode, you look at the 68th percentile about that. And this basically shows that the MCMC and the probability density agrees for that parameter very nicely. So we can actually use the MCMC to describe our PDF, our probabilities. So if we take this to the Poisson data, and this is illustration of the two presentation. One representation shows equal tail of 68% intervals for this spectrum. And you can see that the 68th percentile covers a lot here. And the actual shaded, if you quote uncertainty sort of for the line, it would be between this and that. The equal tail presents a slightly different picture. It basically just shades from the peak. So the peak of the mode is here for that line, and 68th percentile covers also those peaks, other peaks in that spectrum.
Another question. In
Yeah.
the top plot, the lines that are on the left there are not.
No, because you start from the highest peak. Because that's, this is posterior probability density versus energy for the line location. So the most, likely would be at the peak, and then you look at the 68th percentile around that peak. Or I would say equal tail, so you start from the edges and integrate actually. So you get 68th percentile of what's left. In this case, you start from the peak and you go down, and I think in the next slide maybe is a little better. So this is actual, high resolution. That's what we actually used. And then you go from the top, and this is 50 percentile HPD, this is 68, this is 98. So that's sort of 50% level. So you would say, this peak and this peak are probably there. This is maybe the lines at 50 percentile HPD. It's a different interpretation that we typically think about. Yes, Ottoman, it's okay. So this is another visualization of the joint posterior distribution. This is for two different line locations. So one is the full resolution, the other one is the smooth. And this is sort of showing you, how the locations are correlated. I don't think I can talk about it more. And then the uncertainties. So the uncertainty for the line location, so this was the posterior probability density function, and then the location of the line is here with the width, and then this is sort of zoom in and showing the mode and the width of the line. So that's what I think Herman would like to see in publications and maybe in the published things. And the significance of the line, again, if you go and do posterior predictive p-values calculation, you will have, for one type of model, there is the p-value of 0.018, and for the other one is 0.11. This wouldn't be a good significance, while this is significant line, right? Well, and that's the summary. Right, sorry, this was a lot in 20 minutes, and I hope you can go back and read and get details and then ask questions. So,
Right,
thank
cool.
you.
Let's thank Aneta. All right, are there any questions? Yeah.
Very confused.
How applicable is this in cases where you don't know the exact line wavelength?
Yes, so this last application was really for detecting a line location and the width of the line. So Protassov example was for a location which you know a priori, and it was the fit just for intensity of the line. The generalization of Park algorithm is to apply also to the location of the line and the width of the line. So the other parameters come into play. So if you don't know the line, then that's sort of looking for the presence of the line in the spectrum. We haven't tried with the very high signal-to-noise data, which I think is, should happen.
What if you don't really know
That's a problem, then, yes. Because, well, one thing is that you don't know how many lines you have, and you don't know the shape of the continuum. So in the full model, you fit all together, right? So if you go back to the equation which I showed, you had the continuum component and the lines which were not specified. There were k lines, but k could be a parameter of how many lines do you have. So for continuum, if you don't know your physical source for the continuum, you can use polynomials or some kind of function which describes the smooth shape of the continuum. Of course, you can have a situation where you have only lines, right? And that's becoming a more difficult problem, of course. I mean, nobody said that statistics is easy.
Yeah, I think we have time for one more.
question.
It's quick.
Yes.
Let's make it nastier. What if you have blends? Maybe.
What?
What if you have blends?
Oh, blends. Oh, well, then you that's not addressed here, right? You may say there is a probability there are 2 lines or 1, and then you have to somehow put a prior on, let's say, the lines which are close together. I didn't say anything about priors, right? And with the prior, if you may put the constraints on, where the lines are, how many lines do you have, what is the separation between lines. So priors would allow you to do that.
Can I follow up on that just a minute?
Yeah.
So having a blend is not a critical, fatal problem, because generally speaking, the reason you're using this is to figure out whether there is a line or not. And a blended line basically shows up as a broader line. So if you have a parameter that accounts for the width of your underlying line in some fashion, then you can pull that in. So blend, unless it's if there are 2 lines that are like that are separable but overlapping a little bit, then it's generally not a problem.
All right. Well, let's thank both of our speakers.
Oh, pizza. Sorry, I have to undo this.